So we're going to work with our completing the square. We started talking about this yesterday. We practiced finding the pieces we needed for completing the square. And today we're going to talk about how we use this when we're solving stuff, because we didn't quite get all the way to that part yesterday. So this is going to be our first one. We're going to look at x squared plus 6x plus 7 equals 0. And we could try and solve this, by factoring and get our answer that way, but we're supposed to try doing it with completing the square. So we're going to do that. What we're going to do when we're trying to solve by completing the square is I'm going to not have it be equal to 0. I want my stuff with x's on one side and my constant on the other side. So what I'm actually going to do is I'm going to subtract my 7 to the other side of my equal sign. Leave a little space between your 6x and your equal sign. So when I do this and I subtract 7 from both sides, we're going to have our x squared plus 6x, and I'm going to leave a gap, equals negative 7. I'm going to fix that x because that looked weird. So just setting up like this. Because then what we're going to do is we're going to figure out what this number would need to be, so just like yesterday, in order to make this be a perfect square trinomial. Hush your face. So we want to do just like we did yesterday and figure out what number needs to go here to make this be a perfect square trinomial. The way we did that was we took our b over 2 and squared it. So what's our b? 6. What's b divided by 2? 3. What's 3 squared? 9. So we would really like to have, really like to have a plus 9 right here, because that would make this a perfect square trinomial. If I would like to have a plus 9 there, so I want to add 9 to the left-hand side, what do I need to do to the right-hand side? Add 9. I can do whatever the heck I want as long as I do the same thing to both equal signs. I promise there's a reason we want to do this. Have faith in me. Because the reason we did this is so this is a perfect square trinomial. So let's factor this side. Factor this guy down. When we factor this, x in box, using the fact that we physically built this to be something particular, however we choose to factor this, we should get that in factored form, this would be x plus 3 times x plus 3, right? Negative 7 plus 9 gives me a 2. Also, I could write this as our x plus 3 squared equals 2. Yes? The benefit of doing this with completing the square, I'm going to change the view real quick just because I don't want to have to write super duper small, is because now I can solve this with square roots. I could come through here and go, okay, I want to unsquare this. Well, if I square root this side and I square root this side, that's going to get rid of my radical over here, and we're going to be left with our x plus 3, and that's going to equal, whenever we square root both sides, plus or minus the square root of 2. Still wanting to get all the way down to an x equals, so what do we need to do? Subtract 3. So we're going to have that our x equals, and since we have this radical, I tend to just kind of leave the radical on the end. I'm going to put this as a negative 3 plus or minus the square root of 2. You can put the square root of 2 minus 3 and the square root of 2 plus 3. Just make sure it's really clear that it is not the square root of 2 minus 3. Very different thing. Square root of 2 minus 3 is very different than square root of 2 minus 3. So make sure we're really clear. I tend to put my whole numbers in front. It just keeps things very clear of what's outside my radical and what is inside my radical. This gives us 100% the exact same answer we would have gotten by using the quadratic formula. 100%. If I took my A, B, and C and put it through the quadratic formula, we would get negative 3 plus or minus the square root of 2. Okay, so it's a different way of getting to those solutions. The benefit of completing the square is when we're right here, before we did our square roots, we are about a half step away from vertex form. If I made this equal to 0, that would be vertex form. So it's taking other pieces and kind of mixing them around. We're going to practice this a couple more times. Oh, I have coffee. Water. All right, so we've got 2x squared plus 8x minus 5 equals 0. So again, just like we started last time, I want to have all my x's on one side and all my constants on the other. So I'm going to start by adding 5 to both sides. I would like to have our 2x squared plus 8x equals adding 5 to both sides, we get a 5. Ooh, but we have not completed the square when we had an a value other than 1. Shoot. Look at that left side. What can I do with 2x squared and 8x that will leave me with an a value of just 1? GCF of 2. If we have an a value, divide it out. Because this is the same thing. I'm going to write it in 2 steps for. We're going to have our 2 times our x squared plus 4x equals 5. And you can absolutely work it right here. Yes, dear.
If you just went on, could you complete the square by knowing?
You can, you just have to take in consideration the a value, which would be that we would take our, I think it's b divided by 2a. I have to pull it up. It's a little bit more complicated. It changes the number on the end because the a value does play an effect on that middle term. So you could work it right here and figure out this value, but it is going to be slightly more complicated than if I say, ugh, I really want to get rid of that 2 and put it on the other side. What can I do to get rid of that 2 and put it on the other side? Divide. So if I divide both sides by 2, we're going to have our x squared plus 4x, leaving myself a gap, equals 5 halves, or 5 over 2. So even when I have an a value that's not 1, I can manipulate it around, so I do, because that's way easier to deal with than remembering 2 different formulas for how to find that last bit. Because then what we want to do is we want to figure out what we want there to make that be a perfect square trinomial. We want this guy to be a perfect square. So I want this last piece to make this thing be a perfect square. What value are we going to want to have there? What's our b? Divided by 2? Square it. So if I would like to have a plus 4 on this side, that means I need to have a plus 4 on the right-hand side. As long as I add it to both sides, I can do whatever the heck I want. That makes this our perfect square trinomial, so I can put this into our factored form. I'm just going to go straight into the squared notation because that's the one that's particularly helpful. If we factor this properly, and if you want to write it out where they're side by side and then put them in squared, 100% okay. Because we should end up with our factors of x plus 2 and x plus 2, giving us x plus 2 squared. And that's going to equal, what is 5 halves plus 4? Yeah. It's 13 halves, or 6 1/2. 5 halves plus 8 halves. 5 plus 8, 13.
How is it?
If we write 4 in terms of halves, that'd be 8 halves, because 8 over 2 simplifies down to be 4. If we're getting to our common denominator, times 2 over 2. So we have 5 over 2 plus 8 over 2.
Uh,
Okay? All right. So now we're going to come through this and try and simplify. I'm just changing our view again so I can get a bit more space. Trying to solve this down, we want to get to an x equals, what can I do next? Square root. We square root both sides. That's going to give us our x plus 2 equals plus or minus the square root of 13 halves. Ew. What do we do to get x by itself? Subtract 2. So we're going to have our x equals -2 plus or minus the square root of 13 halves. Or you can put our 6.5. Totally fine. Okay. Questions on that one? We're going to do one more like this. Same kind of vibe. So here's our last one of the completing the square stuff. We got 4x squared minus 12x minus 11.
it's funny because we started off with all of them being positive,
Mhm.
and we went on to one being negative.
It happens like that. All right. Knocking this out. What should we do first? Add the 11 is exactly right. I want to get my x's all by themselves first. So we're going to have our 4x squared minus our 12x, and that's going to equal a positive 11. Then what are we going to do?
Greatest common factor four.
We need to take out the 4. In order to figure out what goes here, I need to have an a value of 1. Or that's the only way we've done it. So I need to take out my greatest common factor of 4. That's going to leave me with that x squared minus 3x equals 11. Then what are we going to do? Divide by 4. So that's going to give us our x squared minus 3x. Leaving myself a big gap on this one equals an untidy friend of 11/4. Ew. But fine. It's 2 3/4, but So then we need to figure out what we want to have here that will give us our perfect square trinomial. Yes. It's going to be 9/4. We take our 3, divide it by 2, 3 halves, and then we square it. So 9/4 plus 9/4. And if that's not something we can do in our head, that's totally valid. We're taking our 3, dividing it in 2, so we get 3 halves, and then we square that to get our 9/4. Because divide by 2, and this one has 2 square. I know, the fractions are unpleasant. Because honestly, the fractions are the hardest ones to figure out what the heck our factor is going to be. Because when we factor this, we're not used to factoring when it has fractions inside of it. We'd like to get this directly into our square form. So we know we're going to have an x here. This term is negative, so we definitely need to have a minus here. And then the value it's actually going to be, and if we look back at our previous ones, we can see it when we're looking at our patterns here. And when we're looking at our patterns that we get from here, this number is always going to be half of whatever the b is. So whatever half of our b was. So half of the b is what this is. Whatever this middle piece is, the thing we squared, that's this guy. So this is going to be x minus 3/2 squared. Equals our 11/4 plus 9/4, 20/4, also known as 5. Now we can solve this using our square roots. So if we square root both sides, we're going to get our x minus 3/2 equals plus or minus the square root of 5, because we're square rooting both sides. Add the 3/2. So we'll have our x equals, adding 3/2 to both sides, we're going to get 3/2 plus or minus the square root of 5. Which is, again, exactly what we would get if I took that whole first guy and put it through the quadratic formula. It's the same exact pieces, it's just making a pit stop at vertex form here, because this would let us find our h, subtract this over, we have our k, there's a vertex. Okay? So completing the square is another way to get into vertex form. Okay, those are all the things in section 2-3. That's everything up to there. That's what will be on the quiz. Do we have any questions on 2-1, 2-2, 2-3? You want to talk through real fast? All right, doesn't have to be super fast, but or we feeling okay? Okay? Yes, dear. It does change your what you're dividing by in your completing the square. And I just have to think it for a second because it's been ages since I did it that way. You know what? I better do that. So you can do it without dividing out that GCF. I don't want to tell you something wrong, so give me 1 second. Because I bet the book has it. I just can't pull it up off the top of my head, but I've had too many other things. Yes, it is. It would be b over 2a squared. So you just have to make sure to include that in. It wouldn't just make a GCF here. It would change what value we put in. So if we did it without this, we would put like a 9 here, but we would need to make sure we subtracted like different pieces. Like it makes things a little bit weird. So it's absolutely doable without taking out the GCF. It would just be instead of b over 2 squared that we're putting in, is b over 2a squared. And then it would be b over 2a here. So yes, it's doable without it, but I like to just have ideally one thing to remember at a time instead of 2 different options. Okay. Feeling okay? Okay. Because section 2-4 is very, very, very familiar. You have worked with it before. You might not be super thrilled about it, but we have done it.
I forgot.
That's okay. We're going to talk it through. I promise. So section 2-4 starts looking at complex numbers. So we're going to deal with imaginary numbers. Okay. So what is I? Remember?
Square root of
the square root of negative 1. So I is the square root of negative 1. It is literally something that has been made up. It is imaginary because it's not real. It doesn't exist. I was created because mathematicians were frustrated they couldn't get to an answer, especially on quadratics, when we had negative numbers under radicals. So they invented I so that they could finish the problem. Yes, sir. Yeah, let me write your pass. So what we're going to think about is we're going to think about what happens as we look at different powers of I and going through that. Just 1 second. So take a look at these and see what we think is going to happen for our I squared. So we know I is the square root of negative 1. It's just I. I'm just going to put I. What is I squared going to be? Negative 1. That's our square root of negative 1 being squared. So the square root and the square cancel out. So this just becomes negative 1. I is the only thing that when squared gets a negative number. Only thing. What are we going to get for I cubed? Almost. Not quite. I see what we're thinking. Think about I cubed as being made up of I squared times I. That's the exact same thing, right? What does I squared equal? Negative 1 times I. What we get is actually a negative I. Because I squared is the same thing as negative 1. What about I to the 4th? Positive 1. Because I to the 4th is the same thing as I squared times I squared. Well, that's negative 1 times negative 1. That's going to give us a positive 1. What are we going to get for I to the 5th? I heard it. It was incredibly tentative, but I heard the right answer. If I think of I to the 5th, and I can break it into pieces like I did up here. I could break it into I to the 3rd and I squared. I could break it into I to the 2nd and I to the 2nd and I to the 1st. Or I could do this as I to the 4th times I. That gives me I to the 5th. What is I to the 4th? Oh, yep, sorry. Yeah. Because I to the 4th is just 1 times I. So I to the 5th is exactly the same as I to the 1st. It's just I. What's going to happen for I to the 6th?
Is it going to be the same as I did the 2?
Because again, I could break I to the 6th up into more pieces. I'm just going to switch colors because I feel like I've had pink too many times. I could make this be I to the 4th times I squared, which is going to be our 1 times our I squared, which is negative 1. Well, that's just negative 1. Because I to the 4th is 1. I squared is negative 1. 1 times negative 1. So what do we notice is happening between our two rows here? It's a repeating pattern. I, with any exponent, can be simplified down to be I, negative 1, opposite of I, or 1. Every time. It can be simplified down to one of those options. So when we are simplifying things that have i's, we should never wind up with i's with exponents. It will either have I, negative 1, negative I, or 1. And we're going to practice kind of trying to identify which of these 4 values an I with an obnoxious exponent is going to have. That's going to be our first piece. So I know I get a little excited about i's. If you need a little bit more time writing, that's totally valid. I just see some pencils moving, so I'm gonna give this a second. I find complex numbers kind of fun, so sorry. Ready? Okay, so we're gonna try and simplify these. We're gonna start with I to the power of the 23rd. Heck. The heck is what we were saying there. Helping. Sometimes we're going to get stuff with weird exponents, and so we need to be able to simplify it. So just like I did for the sixth, where I broke it up into chunks, I'm going to do that. Because I do not want to have to count through 1, 2, 3, 4, 1, 2, 3, 4, 1, 2. Ugh, gross. So I'm going to break I to the 23rd into some pieces. And I'm going to pick I to the 20th and I to the 3rd. And the reason I'm picking 20th is because I know, bless you, that I can make 20 with a unit of 4. Because I to the 20th is the same thing as I to the 4th raised to the power of 5, right? And then we still got our I cubed over here. Well, what is I to the 4th again? 1. So that's 1 to the 5th. What's 1 to the 5th? 1. What happens when I multiply anything by 1? It just stays the same. So this is the exact same thing as I to the 3rd. What did I to the 3rd simplify down to be? Negative I. So see what we can do as far as orders of 4 is a good way to kind of remove stuff out. We want to find some multiple of 4 that can come out of there. Let's look at I to the 82. How should we break this one up? And there's lots of choices on the ways to do it. There's just a couple that I see that are probably easy ways to go. Ideally, you want to break this into 2 pieces, one of which is some sort of multiple of 4, and the other one is one of our top 4 powers. 80 and 2. Because 80 is a multiple of 4. 80 is made up of 4 times what? 20. So I could rewrite I to the 80 as I to the 4th to the 20th and our I squared. Because again, we know I to the 4th is just 1. So if we have 1 to the 20th, that's just 1 times our I squared. What is I squared again? Negative 1. So we have 1 times negative 1, also known as negative 1. All right, what do we think about I to the 36? I want a unit of 4. 36 can be divided by 4, right?
Yeah.
What's 36 divided by 4?
9.
9. I to the 4th to the 9th is 36. Sorry, not in the way. It is 36. 4 times 9 is 36. So I to the 4th to the 9th is the exact same thing as I to the 36th. Which means I to the 36 is going to simplify down to be what? 1. 1 to the 9th are just 1. We love when things are multiples of 4s. It makes things very, very easy. Last one is our hardest one up here. because we have to remember that this has a negative exponent. What happens with a negative exponent?
It
Flips into our denominator. So this is really saying 1 over I to the 19. Ew. It's okay, we can do it anyway. So we're going to just look at the I to the 19 part. What is a multiple of 4 that I can get out of 19? 16. So I could rewrite this as our 1 over I to the 16 and I cubed. Because I to the 16 is I to the 4th to the 4th. So that's just 1, so that guy disappears. And we're left with our 1 over I cubed. I'm going to change the view real quick just because I'm about to run out of space on here. So this is the same thing as our 1 over I cubed. What does I cubed simplify down to be again? 1 over the opposite of I. And that is all well and good, except remember that I stands for our 1 over square root of negative 1. And this is going to be something we don't leave radicals in our denominator. So we need to rationalize it.
If it's,
Yes?
it's 1 over negative I, can't you just like eliminate the negative and flip it?
Yes, you can put the, well, not quite. I was going to say we can put the negative in the top, absolutely valid, but we still need to rationalize properly. Because it's not going to be exactly just flip it. Mm-hmm. We need to multiply this by I over I, because I can multiply it by a funny looking 1. I don't have an equal sign here, so I can't do the same side of the equal sign, but I can do a funny looking 1. Or if you don't want to think about it that way, you can think of it as our square root of negative 1 times square root of negative 1, and think about it as radicals, because that's the way we did it when we first started rationalizing. Absolutely valid. When we do that and we multiply, we're going to wind up with our minus I in the numerator and I squared in our denominator. If you move your negative sign up. If you leave it at the bottom, that's totally fine too. But what does I squared simplify down to be again? Negative 1. So we get minus I over negative 1. Last step. What does that simplify to be? Negative I over 1. Sorry, negative I over negative 1. Just I. So we got to be really careful. It doesn't just flip it, because we had 1 over negative I, and it actually wound up being positive I. Yes, dear. I just moved this negative sign up here. If you want to leave this down here, sorry, I'm just switching. If you want to have it down here, that's totally valid. We would just have the opposite of negative 1. Totally fine to do it like this. We're still going to wind up with the exact same answer. I just tend to pull my negative signs out up into my numerator because it always feels weird to have a negative in the denominator. So the first portion of 2-4 is going to be about I having obnoxious exponents. Break them down into chunks that have 4s. We're going to do 2 more problems because I promise they are easy. I know you're going to complain and look at them because they have I's in them. I promise they're not hard. So we are going to look at some complex numbers. Complex numbers are when we have pieces that look like this. 3 plus 4i is a complex number. 2 minus 7i is a complex number. Minus 5 plus 3i is a complex number. Minus 1 plus 2i is a complex number. Complex numbers have a real part and an imaginary part. So we can have real numbers, we can have imaginary numbers. If I have both real and imaginary numbers, we get complex because they're weird and complicated. And if we look at these complex numbers, so these little guys right here, and we look at adding or subtracting them, our 3 plus 4i plus 2 minus 7i, combine them together like they're like terms. What if it was 3 plus 4x plus 2 minus 7x? That we could do. It's not any different because it's i's. We're going to add together our 3 and our 2. What's 3 plus 2? 5. I know, I ask really hard questions sometimes. And then we're going to have our 4i plus negative 7i. Negative 3i. You have just added two complex numbers together.
That's your answer.
That's your answer. Told ya. As I say, if we look at them, they look all weird and scary because they have i's and weird and lots of parentheses. It is 100% combined in like terms. It's just i's instead of x's. Let's look at the right one. It's subtracting. 2 steps if you need to. You can do it in 1 step if you want to. The only time we might need this as 2 steps is if we want to distribute our minus sign. Just be really careful that you do not accidentally turn this into a multiplication problem. If I am distributing the minus sign through, that means it's not that we have smashed them together. It's now a plus. Do not multiply them. It's going to give us a positive 1 minus the 2i. That gets rid of the negative sign in between, but it does not make it multiplication. I had a lot of people on the very first quiz wind up multiplying 2 polynomials together, like big ones, instead of adding. All right, let's combine these together. What do we get when we combine these together? Negative 4 plus I. So adding and subtracting with these pieces is just like with polynomials. Okay? Tomorrow, just because I don't want to try and hop into it right now, tomorrow we'll look at starting to multiply them and deal with operations and do some pieces on there after the quiz. Okay? You guys have 5 minutes to the end of the period. Oh my gosh, look at that. We got time. What? Okay, I did send you a message on Canvas, so make sure you guys check your Canvas messages. I misread my numbers. It's not that I have all but 4 people registered. I currently have 4 people registered. So we need to register. So check your email, the one you have for school, your 500 email, or whichever one you sent to Ms. Bolland on the Google form. Check that. At the very first day, maybe second day. We had a little QR code to the Google form. Or if you've done a IU DC course before, you already have your account. You just need to do the registration part. Okay? So check your email from a message from acp@indiana.edu, or check your Canvas messages. There's a link there that should take you to it. I'm not 100% sure that it works great on phones. Just noticing I use systems, and as I use them for my grad school stuff, not always super great on mobile. But if you do it on your computer or on your Chromebook, it should work just fine. So check that out. Make sure you go through it. Once you go through the registration, if you want me to double check that you're registered all the way through, I can pull that up. Before we get to like the cutoff date, I will like remind us several times. I'll be pulling up the list and double checking things. And then we have ways of manually adding stuff as needed. I say we. Ms. Volland has ways of manually adding things. Okay, so work through stuff. As you're working on stuff, if you're working on homeworks and things and you have questions, please feel free to send me messages, emails, Canvas, Parent Square, whatever, smoke signal, homing pigeon, whatever you got, send me questions. I will be incredibly impressed if someone sends me a homing pigeon with a math question. Please don't send me a pigeon.